All right, good morning, everyone. Thanks for being here. We're gonna kick things off. So my name is Olivia. I'm a product manager with Google Cloud. I'm gonna be joined today by Simon Eskildsen, who is the CEO of TurboPuffer, and Zohaib Ahmed, who is the CEO of Resemble AI. And today, we're talking about how CPU-based infrastructure has emerged as a critical piece of AI and agentic workflows. And we'll start by talking about the shift from training to inference and how it's fundamentally changed infrastructure needs. Then you'll hear directly from leaders in the AI space on how they've been able to architect their AI stacks to take advantage of this change and deliver results for their end users. So, as you probably picked up over the course of the last few days and the last couple of months and years, we're in a huge time of change. So for the last few years, the industry has been focused on training massive AI models. We've now shifted toward inference. This is the phase where trained models are generating real-time results for users, and more recently have started to take autonomous action on behalf of those users. So as the use cases change, so do infrastructure needs. In 2026, this year, the industry is going to reach this historic tipping point where the volume of tokens used for inference is expected to surpass the volume of tokens used for training. This inference inversion is not necessarily because of a decrease in training, it's because of a rapid increase in agentic and inference workflows. Inference requires very different infrastructure needs. We're talking about sustained usage at scale from a broad base of customers and consumers. Power efficiency and latency are key for inference, whereas for training, the raw compute power that you get from GPUs and TPUs was really the main driver of progress. We're in this period where accelerators and CPUs are playing very important roles and working together. To put this into perspective, we'll walk through a very quick, simple example. Let's say we have a user who's looking for a running jacket. If I, as a human, am responding to this request, I may know certain things. I have a foundation of knowledge, my brain. I know some things about running jackets. There's a lot I don't know. So when this request comes my way, I'm going to take certain actions. I'm going to understand the prompt, break it down, think about what I can do quickly, think about what might take more effort. For those high-effort workflows, I may go into these loops where I am narrowing down my list of options, doing my research, comparing and contrasting prices and ratings, and then finally attempting to purchase some inventory. If we're instead using technology to respond to this request, we're actually seeing a very similar thing happening. So on the left, we have our foundation. This is our continuously learning model. And then on the right, we have application runtime. This is what happens when we're replying to that response. This is when the model breaks down the prompt, researches inventory across third-party APIs, optimizes choices, and then finally makes a purchase on behalf of that user. And there's a lot of processes and workflows at play here, but what I want to draw attention to is the mix of CPU-based workflows and accelerator-based workflows. So everything in blue is primarily a CPU-based task. Everything in green is primarily accelerator-based. Of course, things can vary depending on what exactly you're trying to do or how you've architected your stack. Google Cloud is AI ready and offers a wide range of products to handle all of these different types of workloads. From control plane and orchestration, running on our cost-optimized VMs, N-series, all the way to foundational model training on our accelerators, Google delivers performance, flexibility, and choice. And there are three workloads in particular that are driving some pretty massive changes in infrastructure needs. So we're going to dive into these emerging trends today. There are three that we'll talk through. The first, agentic sandboxing. Agent sandboxing has skyrocketed. This is when autonomous agents are running untrusted code in secure, isolated environments. The second trend we'll talk about, data processing. Data processing continues to be critical for enabling inference and agentic workloads, and we're seeing a growing need for faster networking and more storage. The third one we'll talk through today is inference on CPUs. This is emerging as a powerful way to control costs. To start with agent sandboxing. Like I mentioned, when autonomous agents write and execute code, it is often untrusted, and we need a secure, isolated environment to protect the rest of our ecosystem. And we see this use case in both reinforcement learning as well as agentic applications. This requires spinning up hundreds, potentially even thousands of sandboxes per second, and resource needs can vary depending on what needs to occur within that sandbox. Oftentimes, resource needs can be very small, and startup time is usually the key bottleneck. So, how are customers solving this today? GCE offers a variety of solutions that range from fully managed solutions like Gemini Enterprise Agent Platform, formerly known as Vertex AI, all the way down to a more DIY approach where you can directly provision VMs for maximum isolation. And this is a space where our general purpose VM portfolio really shines. We have N-series VMs, which are optimized for TCO optimization with both custom machine types and nested virtualization. And we also have C-series VMs that offer bare metal. This offers higher isolation and fast performance for customers that want to use micro VMs. I also want to draw attention to GKE Agent Sandbox. GKE Agent Sandbox running on Google Axion N4A provides up to 30% better price performance when compared to the next leading hyperscaler. Our second trend, data processing. So whether you're running an AI training pipeline or doing context retrieval at runtime, effectively managing a massive amount of data is critical. Filtering trillions of tokens down to the most relevant ones requires high network bandwidth and a large amount of high-performance storage to prevent I/O bottlenecks. Again, Google Cloud has a variety of offerings designed to help you here. So Google Cloud's managed Lustre is industry-leading in this space, and we've also recently announced new network and storage-optimized VMs. C4N, our new network-optimized machine series, delivers the best networking and best hyperdisk price performance in our portfolio. It also delivers the lowest TCO for any I/O-bound workloads. And our storage-optimized Z-series VMs delivers a large amount of local NVMe high-performance storage running on Google Titanium SSDs. In a moment, you'll get to hear directly from TurboPuffer on how they're eliminating data bottlenecks. The last trend that I will touch on is CPU-based inference. We're starting to see more customers segmenting their workloads between accelerators and CPUs depending on resource needs in an effort to optimize TCO. This requires high-performance compute, memory, and support for specific operations. GCE's C-series VMs are built on the latest CPU platforms from Intel, AMD, and Google custom Axion. Each of these platforms includes purpose-built accelerators to boost inference performance, enabling our customers to see enormous price performance benefits. Later, you'll hear directly from Resemble AI on how they're able to take advantage of CPUs for their inference workloads. All right, now I'm very excited to hand off the mic to our industry leaders who can give you some real-world examples of how they have architected an AI-ready stack with Google Cloud. So now I'd like to welcome to the stage Simon, CEO of TurboPuffer. Thanks, Simon.
Thanks, nice to meet you. Hi. Yeah. So I'm one of the co-founders of TurboPuffer, and am I coming through? Yeah. We build a search engine on GCS and other object storage, and then we cache all of the data on NVMe and in DRAM. This allows pretty exceptional cost performance for search workloads where everything by default sits in object storage, and then when you're actually searching the data, we pull it into NVMe, into DRAM, finally into the L1, L2, and L3 caches. We operate at a trillion scale, so we do millions and millions of writes per second onto Google Cloud Storage. We service lots of queries per second, so this is a way to build an architecture, has been a way for us to build an architecture where we can both serve the stale data really well that sits on object storage, but once it becomes operational, we can serve very, very high QPS. So this is the reason for the name, where it kind of puffs into NVMe and into DRAM. The reason where this fits in the context of the talk here in the age of inference is that these models, as Olivia was alluding to, are hungry to connect trillions and trillions of tokens to these models. What something like TurboPuffer and other search engines allow you to do is to essentially attend to trillions of tokens, which normally don't fit in a context window, by allowing the model to do searches. People sometimes ask me, well, why can't I just fit everything inside of the context window? And the reason is, it usually boils down to these 5 things that I call scrap. So the first one is scale, right? You can't attend to trillions and trillions of tokens like the entire internet or an entire enterprise. You have to somehow use a search engine to find the right tokens to attend to and reason through. The second is cost, right? Attending to 1 million or more tokens is extremely costly, right? This is in the many dollars, even tens of dollars, to operate on that many tokens at a time. So using a search engine, especially one that's built for efficiency, is a really, really cost-effective way to do that. We'll get into some of the examples of companies that do that with TurboPuffer, like Anthropic and Cursor and others. The third is recall. It's very difficult for models to learn how to reason over very, very large context windows. There are very few data sets in the world where you're attending to hundreds of thousands of tokens and you have some ground truth of what it looks like to have a great answer for that, right? Like even if you think about something like the Harry Potter series, right? It's maybe 100,000 tokens, and it's just not enough to reason through if you're reasoning, I don't know, through book club answers or something like that. There are very, very few data sets like that. But with search, we can train the models to search data and see if the answers are correct through lots and lots of hops in a way that can be difficult to do for large context windows. The second last reason to use a search engine instead of trying to stuff a context window are ACLs, right? We're not really in a world yet we can say, here's all my documents, these are the permissions for the documents, these are the permissions of the user, please pinky promise that you're not going to show any documents that aren't ones that this user has access to, right? We're not ready for that. We're not ready for that to not somehow color and disimpression the attention window. So we need something where we have strict ACLs on the tokens that make it into the context window and color the final output tokens from there. The fifth reason that we go to a search engine to attend over lots of tokens is for performance, right? So searching the entire internet is something that can be done. I mean, if you open up Google, it can be done in 100 milliseconds, but you of course can't do that with an attention mechanism that's n squared, right, over that amount of data. That scales down nicely too, even to millions of tokens or hundreds of thousands of tokens, but we can do this a lot faster if we use classic techniques to index data. So examples of the kinds of companies that do this are, for example, Cursor. So Cursor is one of our customers, and of course they have to connect a lot of data, as in code, to models to build the application that they're building, right? They have trillions of documents and lots of individual, what we call namespaces, which are all individual code bases, right? So they sit on object storage, and when Cursor is then actually when someone opens up a code base in Cursor or has an agent operate on it, we drag it out from object storage into SSD and into DRAM. And this means that the first query is a little bit slow, but then over time, as the agent queries faster and faster, you know, it kind of puffs up into cache, and we get much better performance. Cursor is probably one of the largest search workloads on SaaS in the world, and so we're very proud to service them and all of the code that runs through it. Another example of a case study of this that needs to attend to trillions of tokens and connect this into the LLMs is Notion. So Notion is a kind of a wiki software for enterprises, and they have lots of features where they need models to reason over all of the inside knowledge of different corporations. They have 10 billion plus documents and a similar workflow, right? When you open up the dialogue to start asking questions or start searching, they can hint and drag that into cache of an individual node from GCS and then start attending to it with their models and start reasoning through the code base. So I alluded a little bit to this earlier, but the way that TurboPuffer works is that everything by default is sitting in Google Cloud Storage. You could shut down all of the VMs and TurboPuffer would not lose a byte of data. I was on call for Shopify for almost a decade, so this kind of architecture is very, very appealing because it means that VM failures and things like that are never problematic for data durability. So everything sits in object storage, and by default it sits there. Again, imagine a use case like Cursor, where you're not using the code base, you've walked away from your computer, and now it sort of fades into object storage. As we start to query it more and more from an agent or from a user, or searching through that data, it makes it into the NVMe SSD cache, finally into the memory cache, and finally out to the model, right, as we're tending to these often very, very large code bases that we're trying to connect to AI. Over time, we have used a lot of SKUs from GCP. We run in tens and tens of regions around the world, have more than 100 clusters, and across all of these clusters, there's different CPUs available. So we're always very eager when Olivia and others give us research previews to new types of SKUs, because we have, it's very easy for us with this very decoupled storage and compute to try new SKUs and see how they perform. So the C4As that Olivia was alluding to earlier, and some of these other SKUs on ARM in particular, do perform incredibly well for price performance for us, and are the SKUs that we use anytime that we can. We made a graph here too, where we're looking at, as we index all these search workloads, how price performance shifts here. And we can see that there's a wide distribution here, and even some of the older SKUs that actually do quite well. Of course, we try to go off the older SKUs because the maximum throughput is a little bit lower. I'll pass things off to Zohaib to continue.
Perfect. Alrighty, thank you, Simon. My name is Zohaib. I'm the CEO and co-founder at Resemble AI. Told to stand right here. Okay, so what Resemble AI does is we actually build our own models. We build models all the way from generative AI in the voice space, all the way to deepfake detection and what we call verify with watermark. We've been doing this for quite a while, and when we're creating these models, we care a lot about the amount of data that we're consuming to train these models. So there's a lot of data processing that occurs when we are training these models. And there are a lot of feature extraction that's required when we're training these models as well. So one of our foundation models is one that detects deepfakes, one that can tell you whether an image, video, or audio file is actually created by an AI model or by a human being. This is where a lot of interesting things happen around multimodality, around consuming a lot of data, around preparing data sets, around training models from scratch, fine-tuning to particular customer data sets, et cetera. We basically have a variety of different models, and over the course of the last 5 years, we've learned a ton about how to create these models, how to serve them to our customers. So our first model that we put out there, like I mentioned, was a generative voice model. Chatterbox is actually open source, but it basically does really low latency generative voice AI. Super sensitive customers to speed and model serving. So a lot of the models that are served for Chatterbox are on GPUs. Compare that to our deepfake detection model. There are a lot more batch operations, a lot more use cases where there's a higher batch size, but not necessarily a low latency requirements. Similarly, with watermarking, you have very low latency requirements, but you have a model that's much, much smaller to serve as well. So what does this look like in practice? So we use a variety of different Google services. To train our models, we actually use H100s. This is effectively, these are models that are like 3 billion parameters in size. Our deepfake detection model at this point is 3 billion parameters in size. The amount of iterations that we do, we're basically publishing and deploying models on a weekly basis at this point. We're fine-tuning models for our customers. This is where we use a lot of Vertex AI with lower GPU types. We could actually fine-tune these models not on H100s, but rather more efficient compute types. And then we're optimizing with VLLM and TensorRT, and sometimes even porting over to Onyx so they can actually run on CPU-specific CPUs. So where CPUs shine for us, a lot of you have probably heard like a lot of talk about how GPUs are used. Very similar for us. We do a ton of GPU utilization on our text-to-speech generation, on voice cloning, on our large detection models that we've built. And anytime we need really fast, low latency, we rely on a lot of GPUs to do that. Whereas a lot of the CPU optimizations right now are driven by all of the data that we're pre-processing. So at this point, we're training on trillions of data points at this point, and each one of them go through different transformations. There's features that are being extracted, and then that is being used for model training. There's also a ton of lightweight detection models that we can run. So a lot of classifiers that under the hood route to different types of models that make it more effective and more efficient. So for example, one of the more common types of fraud that we're finding right now in the market is document fraud. You can actually take a open source image generation model, feed it a image of your passport, and effectively change the face, right? Now we have models that are really good at detecting forgery of text rather than forgery of faces, et cetera. Similarly, we have a model that can tell you like whether a participant in a Google Meet call is fake or real just by looking at their face in a video in real time. All these models, under the hood, we're basically routing it to different types of models depending on the type of input that we're seeing. And the detection of like what type of input it is can actually be run on a CPU. That's a classifier that doesn't require the H100s to actually run. Similarly, watermarking, there's thousands, hundreds of thousands of streams of audio, video that need to be watermarked. Spinning up GPUs to do watermarking in real time is cost prohibitive. So using CPUs to actually do that and compiling these models with Onyx so they actually run on CPUs is how we go about solving that problem. So I mentioned a lot about how we train these models. What I want to focus on is like the 3 services that I think we use quite a bit. So GKE is like the obvious service that we're using to actually serve these models and orchestrate our workloads here in our VMs. We also are big consumers of Hyperdisk as well as Lustre. But effectively, we can use N-series VMs for data cleaning, transformation, and when our machine learning team is actually training these models, there is a centralized place where all the data is accumulating such that they can fetch that data and train models off of. This goes into like multiple terabytes worth of data that is being accumulated on a daily basis so that we can actually train and fine-tune models on top. This is very, very important for us. For example, there are new generative AI models that come out all the time. In the last week, you've seen models from all the way from Google, but also open source models from open source labs out there. And we're effectively training and generating all of these synthetic data sets on a daily basis to improve our models. And we rely on Hyperdisk to effectively collect all those data sets and train those models on top of that data. So the outcome of this is that we're able to train models much more effectively. So the common fear that we get is our customers come to us and they're running different payloads, different types of inputs to our deepfake detection model. And the concern is like, how do you actually keep up with all the generative models that are coming out? This means that we publish our detection models almost on a daily, weekly basis at most, right? So you've seen like in the last month or so, there have been 6 models that have been published. That's almost like at least 1 per week that actually make it to our customers. Previously, this would mean like multiple weeks of time to iterate and deploy new models. So just the cost savings of orchestrating all of these services together to effectively collect data and then to train with those data sets is fairly significant. So the other result of this is that more and more of inferencing actually can occur on CPUs. So we have spent a ton of time getting our models to actually work on lower types of compute, getting off of H100s so that inferencing can actually occur on either smaller GPUs or ideally CPUs. So one of the models that we're launching on open source is Chatterbox Nano. It's a much smaller version of the model, but it behaves with very similar attributes as the larger version of the model. Most people actually cannot tell the difference between Chatterbox and Chatterbox Nano for text-to-speech. And this is a 100 million parameter model that's been distilled down that effectively gives the same performance as extremely large models that require heavy amounts of compute to run. So this means that you can actually run this on a CPU VM type or even local machines. We've done very similar things with Gemma in the recent few weeks or so. If you haven't tried, you could actually take Gemma and run it on very efficiently on CPU types. But furthermore, you could actually train those models and fine-tune Gemma models for precise use cases. And then those use cases, the entire fine-tuning process, surprisingly can actually run on a CPU. So you're not GPU dependent to even train models, which is a very interesting phenomenon. So what does this mean? So typically, we've spent a lot of time profiling our pipeline. There are a lot of things that could run far more effectively on CPUs than GPUs. We're big fans of Airflow as well, so separating and distributing tasks through Airflow and finding ways to parallelize with CPUs, very, very efficient. We're big deployments on-prem, and through that we've learned that when you're deploying on-prem, you have a ton of efficiency gains that you can have, but you have to actually package your models in a way that you can actually run them on-premise. And so there are tons of learnings there as well. There's a ton of model exports things that we've done, all the way from optimizing VLLM to effectively run really efficiently. We've very painfully become experts in exporting models with Onyx. This has become a lot easier over the last 2 years or so to actually export these models with Onyx to run on these CPU types. So you could actually get models that aren't constrained and locked into certain runtimes. And then the last point here is that there are tons of newer techniques like causal diffusion that compound and get you these infra gains as well. So tons of technique gains that you could have where you're actually able to run these models much more efficiently on CPU types, CPU VMs, rather than just being constrained on large H100s. So that's what I'll leave you with in terms of what we've learned. We've been training these models for the last 5 to 6 years or so from scratch. So there's tons of learnings apart from these 4 that we've pulled apart, but we rely on a ton of these Google resources to effectively make this much more efficient for training all the way down to inferencing so our customers can use our models. With that, I will pass it back to Olivia to take us to the end here.
2 key takeaways in addition to what you've already heard, or call to actions. The first one is to audit your AI stack and see if you can identify these bottlenecks. Like you heard, whether it's CPU, memory, storage, networking, data, Google Cloud has a ton of products and offerings, as do our partners and customers, that can help you overcome these bottlenecks and really turbocharge whatever you're trying to do, from AI inference to more general and traditional workloads. The second one, test the performance for yourself. Of course, your stack is your own, so doing some benchmarking and testing is absolutely the best way to observe the price performance benefits that the latest generation of products can deliver. We do have a few more sessions throughout the rest of the day. I know it's day 3, so there's a few more happening today. And then, of course, many of them have been recorded, so you can always refer back. You can scan that QR code to learn a little bit more about what we have in terms of infrastructure. And the last thing I will ask for is feedback. So if you have a moment to give us some feedback on the session and how Google Next is going for you, that would be awesome.